I have received, or we have received on the several channels we have. So there was one student asking me if I could give a quick recap of model selection and regularization, which I would like to do now. So in one of the exercises, you had to predict cryptocurrency prices. So we had a Bitcoin price, we had a data set containing data points with Bitcoin closing prices and Ethereum closing prices. So we had some data points here. So each of these data points is characterized by a pair of a feature, the Bitcoin price and the label, the Ethereum price. And we would like to use machine learning to predict the Ethereum price for new data points where we only know the Bitcoin closing price. So we want to find a hypothesis which maps a Bitcoin price to a predicted Ethereum price. So Bitcoin input, Ethereum predicted Ethereum price output. How do we move on in a machine learning problem? So what hypothesis functions do we consider, or would you consider for this? Any possible mapping from Bitcoin price to Ethereum price? Yes? Linear or polynomial. So let's say we consider this predictor to be out of a certain space or hypothesis space, which is defined as the set of all polynomials to a certain maximum degree, or with a certain maximum degree d. So the maximum power, the maximum exponent here is the degree of a polynomial. And then we have coefficients, some real valued coefficients, which define a polynomial. What is a good degree here? So d is a parameter of this hypothesis space. What is a good degree? What? 3. Okay, let's say we try degree 3. And we fit it. So how do we choose a good hypothesis out of this hypothesis space of polynomials of maximum degree 3? Or how do we evaluate the quality? So let's say we have such a particular hypothesis out of this hypothesis space. How do we measure how good it is? Yeah? The amount of error, yeah. How do we measure the error? Using a loss function. What would be a good loss function here? Remember, you can choose the loss function mainly on your own. It's a design choice. What loss functions did we use so far? Excuse me? Squared error? Yeah, let's use a squared error. So we look at the prediction error. So we look at the difference between the predicted Ethereum price, which is this here, for this data point. So we have this data point, which has, let's say this is x1 in the first in the data set for some reason, and here this has a label y1. And here we can, for such a label data point, we can evaluate the loss, for example, the squared error loss. So we apply the predictor. This is the predicted Ethereum price for the first data point. And this is typically different from the true price that we recorded. And then we square it. So this is the loss for one data point. How do we combine them all? We sum them up. So we sum this over all points in the labeled data set. So we make here I, and this is the index. And then we use a normalization factor, which is not that important. So this here is the empirical risk. Empirical risk of a predictor over the training set, the labeled training set. And what we do? Well, we pick the hypothesis which minimizes this risk. let's call it epsilon h over x train for the training set. So this is the training set. Training set is a bunch of labeled data points, a bunch of data points where we know the features, the Bitcoin price, and the Ethereum price. Any questions so far? That's mainly what we did so far in this course. Okay, so we minimize. Let's get a bit order here. So we minimize the training error. And what we get out of this is a particular hypothesis, a particular polynomial. So let's say this is minimized by h hat. So this is the polynomial which minimizes this training error. Let's say this is this h hat. How can we find h hat? How can we solve this empirical risk minimization problem here? For example, using gradient descent or closed form expressions involving some matrix inversions. Okay. So the question now is, are we happy? Are we finished? Once we have solved, we have managed to implement gradient descent, it shows a nice behavior, the training error goes down, is very low. Are we finished? Yes? We have to test or we have to validate it on new data. In the end, we are not interested in how well the predictor, h hat, is in kind of imitating the training set, but we want to know how does it perform on new data. Like this, let's make the circles here. This is new data. So there are some new data points coming in. For example, I get the Bitcoin closing price for today and tomorrow. Somehow I manage. But I don't know the Ethereum closing price for today and tomorrow. Well, then I use exactly this predictor to plug in the Bitcoin price. So here, Bitcoin price of the new data point, and I get a predicted, this here, this is the predicted Ethereum price. And the question now is, does the predictor also work well on this new data? And for this, we need to have some new data, so to say. And this new data is also called validation data. So we use another data set, another set of labeled data points to validate the predictor. The important thing here is we don't minimize, or we don't optimize the predictor over the validation set. We only optimize over the training set. Over the training set we optimize. And that's why the error that we get here, so this minimum empirical risk over the training error, is too optimistic often. Because this quantity is exactly what we try to minimize by choosing h hat. So it's a bit unfair to use this training error to evaluate the quality of h hat in general. Because this h hat is does exactly the job of minimizing this training error, but not more. So we have to make sure that it also does well on new data, on validation data. And that's the basic idea of validation. If you have a data set, so let's say this is our data set, which contains a bunch of labeled data points, split it into two subsets, where one you use as training set. So this one you use to formulate the empirical risk minimization problem. So over this data set, you run this minimization problem over X train. And this other one is the validation set. Here, so this one produces, implementing this empirical risk minimization means to learn. This learns a predictor h hat, which you get using gradient descent, for example. And then we evaluate h hat, so the empirical risk, we compute the empirical risk of this h hat on the validation set. So first we learn a predictor on the training set, and then we evaluate the predictor on the validation set. Yes?
Does it make sense to train, so we decide one degree and then we train the model or the hypothesis and then we decide for the degree according to the validation set?
So the question was, can we then use this validation error to optimize the degree? Yes, exactly. That's what we do then. So using this validation error tells us in some sense how good this hypothesis space here is. So this validation error is kind of a loss function, a higher level loss function for a hypothesis space. So this here, this empirical risk, measures the quality of a particular predictor. This validation error measures the quality of a particular hypothesis space. So in some sense it's just going one level above, making a hyper-hypothesis space whose points are polynomial hypothesis spaces. And we use the validation error as an empirical risk for this hypothesis space. So we can say model selection then amounts to working on a hypothesis space whose points are hypothesis spaces. So we have the set of linear functions which are polynomials of maximum degree 1, as many of you found out. So degree 2, degree 3, and we do again the same principle. We try out different hypothesis spaces by fitting a hypothesis space using empirical risk minimization and a training error, and then we evaluate the hypothesis space by looking at the validation error. We try this out for all the hypothesis spaces here and pick the one with the smallest validation error. Yeah?
What was the name of the
H-hat? Yeah. This is the predictor which has been learned by empirical risk minimization. It's kind of, if we use as hypothesis space a polynomial space, then this would be the optimal polynomial on the training set with degree d. Or if this hypothesis space corresponds to a deep neural network, then this predictor corresponds to the best choices of weights inside a neural network. So this is just one particular predictor out of the hypothesis space, the particular predictor which minimizes this training error. It's the predictor that we learn by solving the training problem, by doing training. And after we have learned this predictor, we evaluate or we measure its quality on the validation set. Yeah? So the question was, does the training set have to be a smaller set and the validation set a larger set? So this question is referred to the optimal split ratio. So how large should we make this training set compared to the validation set? And unfortunately, there is no widely applicable general rule. There are some rules of thumbs like 70%, use 70% of your labeled data as training and 30% of validation. But what the optimal split ratio is, that is, what is the optimal share that you should use for training data and validation data, depends on so many factors that you have to try it out by trial and error on your data set. Yeah?
How do you evade the outlier to get the model?
Sorry, what was the...
How do you evade outliers to get into your model?
How you evade...
Outliers.
How you evaluate outliers?
Evade. Like the outliers do not affect your model.
Well, the outliers, so the question was how can we avoid that outliers affect the model? Well, we hope that these outliers get caught then by looking at the validation error, that the validation error is large. So, but there are more specialized methods for detecting outliers. Any other questions? Okay. Then I was also asked to give a bit more backward information on regularization. So this is model selection. We train on a training set and evaluate the resulting predictor on a validation set. And why we do this? Because we expect the training error. So the training error is the minimum of the empirical risk minimization problem. So if we solve the empirical risk minimization problem, by computing the empirical risk of the predictor over the training set, then what typically happens is that this minimum value, so this yields kind of an optimal predictor. This is argmin. And if we then plug in this optimal predictor here, then we get the minimum objective function. This is the minimum without argmin. It's also interesting to look at the training error. So the training error is, let's denote that E-train, is the training error evaluated for the optimal predictor on the training error. And already this formulation hints at that this is optimistic. This is an optimistic error measure because we exactly tuned this predictor to make this quantity small. And we expect that the validation error is typically larger. So what do? We add a term, a regularization term, which depends on the predictor, which kind of anticipates or estimates the increase that we expect to get in the validation error. So instead of minimizing the training error, we minimize the training error plus the anticipated increase in validation error. And there are different choices for this regularization term. For polynomial regression, in polynomial regression where we can parameterize a predictor using a weight vector, like this. So these entries of the weight vector are the coefficients of the monomials, are equal 1 to d. And it turns out the larger these weights are, the more, let's put it here, the more wobbly or wiggly the function is. So if the weight vector is large or it has a large norm, then this corresponding predictor or hypothesis, polynomial, this polynomial function is very wiggly. So we expect for the large weight vectors that if we fit it well on labeled training data, it might not do a good job on validation data. So the validation are the circles here, and the crosses are the training data. And if this norm here is large, so we have several large coefficients of a polynomial, then the polynomial tends to go crazy. And therefore we expect for a large norm to have a large increase in the validation error, and we take this into account by adding the squared norm of the weight vector. Okay. That's regularization. Then we allow here a tuning parameter lambda. So this we can tune. Here we use our intuition or some prior knowledge that tells us how wiggly will this polynomial be. But in the end, it's just a parameter which we could say defines a different hypothesis space. So we can kind of define this objective function as a loss function underlying a hypothesis space which is indexed by lambda. So we have a continuously indexed set of hypothesis spaces instead of a discrete set of hypotheses, like when we choose different degrees, degree 1, degree 2, degree 3. So we have a discrete set of different hypotheses. But here we have a continuous parameter which allows us to fine-tune the different to kind of continuously change the underlying hypothesis space in some sense. So how can we choose then a good value for lambda? So we solve this regularized empirical risk minimization problem over the training set, and we get a predictor out of it. How do we evaluate the quality of the predictor? Using the loss over which set? Oh, the validation set, yeah? So we try out different values for lambda, say lambda 1. We get an optimal predictor which solves this. So this here is now parameterized. We have one different risk minimization problem for each value of lambda. So this is now This optimization problem is parameterized by lambda. For each choice of lambda, we get typically another optimal predictor, regularized predictor. And then, so we compute these regularized predictors, lambda 10, and so on, for a bunch of different values of lambda, and we evaluate the quality of those using the empirical risk over the validation set. And guess what? We then pick the value of lambda which yields the smallest validation error. Okay. Any questions on regularization model selection? You find a more detailed discussion of this regularized optimization problem or regularized empirical risk minimization problem in the course book. And there it's also detailed that adding this squared norm of the weight vector has also a pleasant effect on the difficulty for solving this problem. Because when you use polynomial regression here, then you can write down this empirical risk as a squared norm of a label vector minus a feature matrix times the weight vector. And adding this term here, the squared norm, has a positive effect on the ease of solving this problem, either using gradient descent, you can use again gradient descent, or you can use a closed form expression. And the closed form expression that you get here always works if this here is non-zero, if this is larger than 0. Remember, for plain linear regression, we ended up with a closed form solution which involved a matrix product of this form x transposed x, which we had to invert. And but we have no control over the feature matrix. So it might well be that this matrix is not invertible. However, when you derive the closed form solution for this optimization problem, you have to invert a matrix of this form. So you add a scaled identity to a positive semi-definite matrix. And in your basic linear algebra course, you have learned that such a matrix is always invertible. And actually, there was one quiz question in round 1, if I remember correctly, which asked you specifically about the properties of such a sum of two matrices. Good. So I hope this recap helps you better to understand the very simple idea of validation and regularization. It's very straightforward. Just try out the predictor that you get from the empirical risk minimization over a training set. Try this predictor out on another data set. And there are different ways to construct this other data set. The most simple way is to split your entire data set into a training set and a validation set. But you can also repeat this procedure several times and randomly shuffle the data in between. This is then called k-fold cross-validation. But the basic idea is the same. Split the data into a training set and a validation set. Okay, so there was also a very interesting question at Slack which asked, what is the difference between the models or these function-based methods? We use functions, so we have predictors